Ladies and gentlemen, hello and welcome to the KEMET webinar on lifetime calculation. My name is Alexander Nebel and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter today is Jekaterina Stael von Holstein, our field application engineer in Central Europe. Hello Jekaterina, thank you for presenting today. Please tell the audience shortly about your role inside KEMET and then you can directly start your presentation.
Thank you very much, Alex. Hello, everyone. My name is Jekaterina Stael von Holstein, and I'm a relatively new KEMET field application engineer in Central Europe. I freshly graduated from university with a master's degree in power systems engineering in October, and since beginning of January, I worked at KEMET. Today, I will hold my second webinar for today's topic, Not All Lifetime Calculations Are Created Equal. The reason why this topic is essentially interesting for designing, for R&Ds, as well as for the technical support, is that the lifetime of a component has to be considered regarding the conditions under which an application is operated. In particular, for short-living components, the lifetime can be increased when operated smartly, and therefore maybe also a different part can be examined for the application. Besides, for power and industrial applications, the efficiency and the value of the component are of great interest, as reliability plays a big role while designing an application. In this presentation, now I should go. In this presentation, I will talk about lifetime of capacitors. In order to have a visual example, I have chosen DC-link application, and therefore I will explain the lifetime calculation, especially for DC-link capacitors. But I want to stress that the following information on calculation is also valid for all other types of capacitors. For each capacitor type, lytic, film, tantalum, MLCC, I will shortly show the series examples and explain how the technology is affected in its lifetime due to its internal construction. I will also show you for each capacitor type the used equations in general and the values which essentially influence the lifetime of the capacitors. Afterwards, there will be real examples demonstrating how to use information from our datasheets and our tools from the engineering center in order to determine the lifetime of a component. Afterwards, I will also explain what fit rate is and how to calculate it. So let's start with our example, which will be helpful for our further considerations, the DC-link application. A DC-link capacitor in between a DCDC and DC-AC or AC-DC and DC-AC converter is essential for the balance of instantaneous power variations between the input and output sources. This is how load changes are minimized, and the DC bus is supported by supplying high ripple currents or switching circuits. The main requirements for the capacitor are therefore low ESR and low self-inductance, high ripple current ratings, and life expectancy. And here we start our considerations at life expectancy. When we think about DC-link capacitors, very fast lytic capacitors come into our minds. Here we have a small overview of capacitors. It starts with axial radial ground capacitors, then goes to big elcos with snap-in and screw terminals or press-fit capacitors, and continues with SMD capacitors. They all have different values and purposes, but of course they are all based on the same technology. The electrodes of lytic capacitors are both made of high-purity aluminum foil, but the electrodes have different thicknesses and also different edges. And on the surface of the anode, there is for at least for the standard lithium capacitors, an aluminum oxide film dielectric, which is wet. And this wet dielectric essentially determines the lifespan for standard lithium capacitors. For polymer lithic, a conductive polymer material is used as electrolyte, which highly influences the behavior of this capacitor in a different way. In general, the benefits of lithic capacitors are basically the high power efficiency, the relatively low costs, and that in case of failure, they do not go into short circuit. But the ripple current capability is low, and the operations under high frequencies lead to capacitance fall. One of the biggest disadvantages is their short lifespan. But before we go on with the lithic capacitors, what is actually lifespan? How is the lifetime defined for a capacitor? Well, unfortunately, I have to give you the answer that each manufacturer has its own definition for the end of life and how to define lifetime. And even the same manufacturer may have for different product types, different definition. But basically, there are three general types of failures. The first one is the catastrophic failure, where an open or short circuit is the result. Besides, there is a mechanical failure where safety vents are activated. And then there's the parametric failure, where the capacitor is fully functioning but its operating value are no longer in specifications, which can be found in datasheets. So what does it mean for lithic capacitors? The lifetime is determined by the ambient temperature, the hotspot temperature, the operational voltage, and the ripple current, which enhances the temperature of the capacitor due to self-heating. The end of life of lithic capacitors are determined by capacitance derating from initial value in percent, the ESR value, and the leakage current. It has to be mentioned that each series may have a different specification for end of life, so please refer to datasheet or to your local KEMET FIE. Yeah, the equations behind the lifetime calculation of lithic capacitors are the following. Please don't be afraid, I will explain them one by one. It can be seen on the right side, a standard model for static conditions, which explains the equations. The total thermal resistance together with the generated power is the difference between the hotspot temperature of the component and the ambient temperature. The lost power is the product of current to the square and the ESR. Of course, in case of current at different frequencies, the sum of product of the ESR and the current at each frequency has to be calculated individually. The operated life is then calculated using the outcome of the hotspot temperature. Therefore, the Arrhenius law, or better to say its derivative, is used. A, B, and C vary for different lithic technologies and series and are therefore given parameters. If capacitors are operated below the rated values, such as voltage, the lifetime rises. So let us continue and use a real-life example. The axial capacitor PAG130 series is used for the application with 80 degrees C ambient temperature at 5 kHz frequency with a ripple current of 5.9 amps. For lifetime considerations, we first take a look at the datasheet and the values for our part. The ripple current at 5 kHz for 105 degrees C, our rated temperature, is 2.7 amps. And the ratio of 5.9 amps, which is the given current of application, and the ripple current, the 2.7 amps capability at 105 degrees C, gives us, together with the operated voltage, the lifetime value, which is given by the graph from the datasheet. In this case, it is exactly 80,000 hours. But take a look, if we operate at exactly the given temperature of 105 degrees C at maximum ripple current, our lifetime is reduced to 40,000 hours. On the other hand, we can increase the lifetime of the component by operating at low temperature of 70 degrees C, even though using the whole ripple current capability. That means for all developers out there, cooling of electronics and derating can really help to prevent a lot of issues. Another example for logic capacitors I want to show you are SMD standard logic and SMD polymer capacitors. Both of them have given indicators of 105 degrees C and 2000 hours lifetime, but of course there are differences. The first one is the calculation method. For every 10 degrees C, the lifetime doubles for standard logic capacitor, while for polymer, for every 20 degrees C, the lifetime is 10 times higher. The reason is the chemical reaction of the capacitor, which speed is increasing when the temperature rises. As polymer electrolyte is not evaporating that fast with the temperature, the life expectancy is higher. Due to polymer technology, the ESR of the capacitor is lower, allowing also high ripple currents capability of the component. Also here, I would like to highlight that with the lower temperature of 85 degrees C in comparison to 105 degrees C, the life of the component rises to 20,000 hours, and with 75 degrees C, it is even 10 times higher. Now here is another example. For our DCDC application, we need 180 microfarad capacitance, a voltage of 500 volt, and we operate at 10 kilohertz, expecting a leakage current of 3 amps. Looking into the component edge on our website, we decide that this snap-in capacitor ALA 8D with the following values meets the best our requirements. But we have different environmental conditions we have to consider. In order to calculate the lifetime, we can use our aluminum electrolytic capacitor life expectancy calculator, which is the best choice in this case. After choosing the component from the drop-down menu, we put different conditions into the tool. So for 20% of time, our ambient temperature will be 70 degrees C and we operate at full voltage. Also, the frequency might vary, like 9.9 kilohertz to 10 kilohertz, and therefore also the according ripple current varies. For 50% of time, we have a higher ambient temperature, and for 30% of time, the voltage drops slightly while the temperature rises. The thermal resistance of our component, as well as parameters such as core temperature for each condition, can be seen in the results section, giving a total life value of 16,200 hours. All calculations are based on the equations given from the slides before, and this tool gives us an opportunity to calculate the lifetime considering real life conditions, giving us a more accurate lifetime expectation. Now, I talked a lot about lytic, but also for film capacitors, the lifetime under different conditions varies, giving limits for the reliability of the component. In comparison to lytic capacitors, the applicable voltages are in general slightly higher, and also the lifespan is higher. But in general speaking, film capacitors have lower ESR and self-inductance, and they have self-healing properties, which is great benefit towards the other technologies. But they have less power and in general may be less cost efficient. Just as example, here are two different film capacitors. the box type C4AQ and the cylindrical type C44UM with the typical applications like solar converters, welding applications, motor drives. Similar to lithic capacitors, we have a roll and a box or a can, but each film layer is metallized, and we do not have a fluid for most capacitors as the electric. As for the lifetime, similar consideration as for lithic capacitors like Arrhenius flow can be made. Let's just go to the example. For our DC-DC application, we need 450 microfarad capacitance at 990 volts, and we have a ripple current of 60 amps at 10 kilohertz. Our temperature in the application is with 45 degrees C low and a lifetime of 100 kilo hours, as a 100,000 hours is essential. Looking into our component edge website, we find the C44UM capacitor, which is an aluminum can type design with a screw terminal. And we can see that all conditions are so far met. Now we have to find out the lifetime to see if this capacitor meets our full requirements. For further considerations, we need the ripple voltage, which is calculated using the ripple current and which is then added to the nominal voltage of the application. If we look at the datasheet of our CC4UM, we meet the ripple current as already mentioned, and we can read the values of ESR and the thermal resistance at given frequency. The power losses are calculated like for lithic capacitors, as well as the hotspot temperature of the capacitor. And as the reference temperature for this capacitor is 70 degrees C, we can continue with the next step. The datasheet of our capacitor has a lifetime curve included. For the total voltage to capacitor rated voltage ratio, which is approximately 0.9, and with approximately 70 degrees C, the life expectancy of the capacitor is around 120,000 hours, which totally meets our requirements of 100,000 hours. I would like to highlight that at the same voltage ratio and a higher hotspot temperature, for example, for 85 degrees C, our life expectancy goes down to 30,000 hours, while exceeding the rated voltage also leads to high life expectancy loss. As promised, I will later tell you more about FIT, but we can also see in this graph that the higher the temperature, the higher the failure rate, and therefore the higher the value of failed parts per billion. KEMET is the first to provide a life expectancy model for film capacitors under harsh conditions, including humidity considerations. And this gives the opportunity to provide the best solution with a real mission profile application. The KLM tool has launched only 2 months ago and is now part of our KSIM 3.0 tool calculator. And so far, 3 AMI capacitors for harsh conditions are included: the F862, the F863, and the R41T. In future, also other capacitors such as DC Link will be included for harsh conditions. The lifetime calculation is a function of temperature, of relative humidity, and voltage, which exact calculation we will not provide. And here's an example for this tool. We have an R41T, 100 nanofarads, 300 volt, which is operated under 2 different temperatures and relative humidity for 50% of working time each. And here we also see that film capacitors end of life is considered to be 20% derating of capacitance, leading to a life expectancy for these capacitors under these conditions for 1.4 years. So also here, cooling and voltage derating, as already mentioned, would lead to higher life expectancy. Now let's go to tantalum technology. There we have standard tantalum with mangan dioxide, dielectricum, and polymer, which is called at KEMET organic capacitor, or CoCap. The difference of dielectric leads to several benefits, which includes preventing of ignition and higher rated voltage operation, but also lower ESR and higher frequencies operations at the same capacitance. The tantalum capacitors are used for DC applications, and polymer capacitors below 75 volt and capacitances with up to 1000 microfarads. By the way, KEMET is #1 producer of polymer tantalum products. I had to highlight it. Our standard polymer series can be seen here. This is the T52 and T53 series, which include high temperature series, high capacitance series, and reduced volume series. But also for automotive, we offer a polymer portfolio with ACQ200 qualification. And for this capacitors, the operational life plays also a big role, and this is why the T599 for 150 degrees C with 2000 hours under harsh conditions has been launched for the market a month ago. This product is the first on the market of its kind and meets the high demand for components in powertrain and high humidity applications. The life expectations for CoCap increases when application voltage and application temperature are lower than the category voltage and category temperature. And for 90% of rated capacitance and rated voltage and lower temperature than 85 degrees C, the life expectancy is then higher than 10 years. As you can see also here, the Arrhenius equations are used for the calculation. The lifetime of tantalum capacitor is defined as failure due to leakage current or short failure mode. And of course, this calculation is all previous before just an estimation based on empirical results and is no guarantee. Here are the values for a polymer 105 degrees C, 2000 hours capacitor. Under nominal conditions, 105 degrees C and full rated voltage, we have an estimated life, as already mentioned, of 2000 hours. And with lower temperature and 90% of rated voltage, we have a life expectancy of already 14 years. Similar considerations can be made for standard tantalum capacitors and 60 to 50% of rated voltage. Also for MLCCs, the equations are valid for lifetime calculation, but the lifetime of ceramic is due to its hard material and solid dielectrics, actually millions of hours, and only the insulation resistance drop may decide about the lifetime. And now let's come to the interesting fact: the MLCCs have a really slow aging process. This is why parametric failure is difficult to be defined. Aging is the decrease of capacitance over time and starts with the first heating above 130 degrees C, which appears during soldering. COG as class 1 dielectric does not have any capacitance loss and is therefore the best capacitor for all applications where capacitance accuracy is important. Good example are applications with oscillation network. X7R have 3% capacitance loss per decade hour, and X5R have 5%. The most significant losses appear within the first 36 months. And this can also be seen in our KSM 3.0 tool for ceramic capacitor aging simulation. The drop is the highest during the first 3 years. Afterwards, it is linear decrease which can be observed. This calculation tool is valid for class 2 and class 3 dielectrics. But in order to visualize how slow the capacitance of ceramics drop, here an example. In the first year, the capacitance jumps very fast from 100% to 97%. After 10 years, which is a typical life expectancy for a lot of electronic applications, the capacitance drops to 94%. In 100 years, and this is when KEMET was found, we reach 91% of capacitance. Assuming that an MLCC was built in the year 0, we would still have 88% of capacitance. Another fun fact, if a capacitor was built during the Big Bang, we would still have 71% of capacitance. So a lot of other facts have to be considered when using MLCCs, but lifetime is not necessarily a necessary one of them. Finally, I would like to come to another topic, fit or failure rate. The fit gives a number of failed parts out of 1 billion. And the calculation is given by the handbook MAIL HDBK 217F. Each capacitor technology, but it's also valid for all other passive components, is included in this handbook. And for them, also different conditions are described with the according values. The conditions are described by the factors which are determined by the temperature, capacitance, rated voltage, series resistance of the component, the part quality according to the handbook, and the environmental factor. As under very restricted conditions, the failure rate rises. For the fit rate, KEMET offers a fit calculator to download on our Engineering Center page. Connected to fit is also the mean time to failure. It is the inverse of the fit and gives the length of time for a part to fail while operated. So let's come to the last slide, the conclusion of this webinar. The main calculations for lifetime calculations are based on the Arrhenius law and also on the acceleration equation by Prokopovich and Vasquez. The results of the results are all estimations and are based on empirical results. The equations vary based on product type and even part type, and also depending on the applications, the values may vary. Manufacturers therefore use different approaches, and our competitors may use slightly different equations and parametric specifications. The fit determine failure in time with the MIL HDBK 217F handbook and is an approach to unitize the fit calculation for each technology for better comparability of the parts. For more information, please go to our website, to our KSIM tool and our Engineering Center webpage. And of course, do not hesitate to ask your local KEMET FAE or product manager. So thank you very much. My name is Jekaterina Stael von Holstein, and thank you for your attention.
So Jekaterina, thank you for presenting today. I hope to see you soon again.
Thank you very much, Alex.
Goodbye.
Bye.